Yes, hello. Here I'm Sebastian. I'm responsible for marketing and welcome everyone. For this webinar, Barett is going to talk 45 minutes about achieving cache level performance without storing data in RAM. But before we do a proper introduction, we're going to give it a few more seconds because I see people are dropping in. Yeah, many people.
Yeah.
So
Hi, everybody. I also see some familiar names, some ex-colleagues. So welcome. I'm very happy that you are here. Uh, so we are going to wait a little bit longer, I guess 2 more minutes for
yeah.
people to join before we start.
So just out of interest, you you guys can see the chat box. Maybe you can post where you located. This is always interesting to see where you guys are all spread all over Europe. By the way, I am in Barcelona, but I'm not Spanish. I'm German. We're gonna have a nice meet up here
Nobody could
tonight.
say that if you didn't say you are German, nobody would have guessed.
Yeah, but I realize walking through Barcelona, everybody speaks Spanish to me, so at least I don't look like a tourist, which I'm not, sadly. Okay, still people coming in. That's very good. So yeah, so welcome everyone. My name is Sebastian Emmerling. I'm responsible for marketing at Aerospike in the Europe region, and thank you very much for attending this webinar. We're going to record it. Yeah. So if you miss something or if you want to rewatch or share it with your colleagues, I will send around the recording afterwards. So no worries. You can also see a chat box up, and please post any questions or comments, and we will discuss that when Barett is finished with the slides at the end of the webinar. Yeah, this is about it. I leave it up to Barra to introduce yourself and to get started. Yeah, looking forward. Thank you,
Yeah,
Barra.
thank you very much. So again, hi everybody. My name is Barett Babaee. I'm a principal solutions architect in Aerospike. My background is I've been a developer for most of my career. Some of the people in the audience, we work together. Pete, hi. I've worked in financial services for a number of years. Before that, I was in IoT and industrial automation field. But in the past 7 years, I've been working for different NoSQL databases. And Aerospike is another NoSQL database company that we are going to talk a little bit about it. It is not necessarily only about Aerospike. We are going to talk about this concept that may sound a little bit strange. But before I want to start talking about the concept, I just want to tell you a quick memory. I remember when I was a kid, when I wanted to watch TV, the TV, if you like the program and you want to watch that program, you had to be in front of the TV at the exact time. Possibly there were a couple of repeats for that program as well, but if you missed that, there wasn't any other way to watch that program that you wanted to watch. Remember at the time, I was a little boy. I went to my brother, who's older than me, and I asked him, well, it would have been great if you could watch these programs on demand. And I remember my brother laughed at me. And I exactly remember this because I mean, one of those memories that you never forget. He laughed at me and said that it's impossible, for TV to be able to show you something on demand. The antenna that is sending the signals to TV sets should send a different signal to every TV set in the country. That's almost impossible. You cannot have TV on demand. But well, 30, 35 years later, everything that we watch now is almost on demand. I mean, everything is possible. So, the technology landscape is moving very, very quickly, and things that we think are impossible are becoming possible and and also becoming the norm. So this topic that I'm going to talk about is kind of like that. I'm going to talk about how we can achieve a cache level performance without storing data in RAM. We usually store data on RAM to improve the performance, but uh, Sebastian, can you mute yourself, please? Thank you. So we usually store the data in RAM to achieve the great performance, but we want to talk about that is it possible to store the data on something cheaper like disk and achieve the same level of performance? So this talk is going to be about that. So if you're ready, let's fire up the engines and basically get on this journey to learn how we can do that. By the way, I spent around 1 hour to create that animation that you just saw. So I just want to show this to you one more time because, yeah, it's 1 hour of my time creating this. Just look at it. It's glorious. There you go. Okay. So if you want to store data on a computer, you have two main different storage places. One of them is memory, the other one is disk. And these two storage components have some opposing characteristics, right? So, for example, the memory response time is very, very fast. It's working in order of nanoseconds, accessing to the memory. But accessing to disk is in order of microseconds, right? So it's like 1,000 times slower. And this misconception that, oh, if you need fast, you have to keep everything in memory if you want. This cannot be fast is basically coming from the idea that it's nanosecond, this is microseconds. Another difference is that memory has a massive throughput, right? So the modern modules can handle something around 50 to 60 gigabytes per second of throughput. When you go to disk, it's lower. Disks have been improving in the past 20 years. Currently there are disks in the market that can handle around 14 gigabytes per second, but it is still, around the order of magnitude slower than memory. The other thing is expensive memory, and the disk is relatively cheap. I actually found something on Amazon, and I just wanted to show you to get an idea. So 128 gigabyte module is around 1,000, about 1,100 pounds at the moment, and you can buy it and you can receive it basically with the next day delivery from Amazon. So if you look at the price per gigabyte, it's something around $9 to $10 per gigabyte for RAM. But if you go to disk, this is one of the fastest disks that you can buy at the moment. This is the 14 terabyte speed 14 gigabyte speed that I told you about the fastest disks that are available in the market. A 4 terabyte module is around 610 pounds. So this is roughly around 15 pence per gigabyte. So that was 9-10 pounds per gigabyte. This is 15 pence per gigabyte. So if you go back here, you can see RAM is significantly more expensive than disk. The other thing is that memory is limited. As you saw, it was 128 gigabyte. Disk is significantly larger. We had a 4 terabyte module there. There are 8 terabytes, 16 terabytes, and then you can have multiple of them on a single machine as well. So you usually have significantly more disk on a single machine in comparison to the amount of memory available to you. And then lastly, disk is persistent, meaning that if you write something to the disk and you turn off the machine and you turn it on again, the data will be there, but memory is volatile, meaning that if you write something into memory and turn off the machine and turn it on, the memory will be wiped clean. So basically the data is going to be volatile on RAM. So when you're creating a database system or well, any other system that need to store some data, you need to pick and choose different data structures, and depending on these characteristics of disk and memory, you have to place them on these modules. So let's have a look at what you need to do in terms of storage requirements for databases. So first thing is that you need to store the data somewhere. So that is possibly the most simple one. The data needs to be persistent, so the data has to go to the disk. So we store the data store part of the database is going to be stored on the disk. The other thing is the primary index. So you have a primary index in any database that you are familiar with. So the primary index enables you to query the data given the queries that you are sending to the database. So the primary index, because it's a data structure that by inserting the data is getting updated, and whenever you want to read, you want to very quickly find the data. It's better to be stored somewhere that you have massive throughput to it and the access time is very low. So therefore, for that, we usually keep the primary index in memory. Another module that requires a storage is secondary index. So again, very similar to primary index. So secondary index is usually stored in memory as well. And then the last component that is very common between databases is a cache. So basically the cache says that if a data was written recently or read recently, keep it in memory. So if a request comes in, you can answer it from the memory that is faster instead of going to the disk that is slower. So usually cache is also stored in memory as well. So this caching idea is to improve performance, but it's possibly not the way that you are thinking about it. And I want to talk a little bit more about that. So, in a computer, you have a bunch of memory and a bunch of disk. Usually the disk is significantly larger than the amount of memory. And when you create a database on top of these data storages, the thing that is going to happen is that your database is going to receive a bunch of requests. And then some of these requests are going to be available in RAM and you can respond to them very quickly, but some of the requests are not going to be in RAM, so you have to go to the disk. It's going to take significantly longer to get the data from the disk, and you respond it back from the memory, and some of the requests are going to be significantly faster, and some of the requests are going to be significantly slower. So because of this, usually people thinking that increasing the amount of memory that is dedicated to cache, either by allocating more of the memory to the cache or increasing the amount of RAM on your machines, you can improve the performance of the database. But this is not necessarily correct. So for that, I need to explain something to you, and it's basically how we measure response time. So think about response time. To explain response time, think about this. So imagine I start logging the requests that I'm sending to my database over a very long period of time, let's say 1 year. So all of the requests that are being sent to the database, I log the time that it took for them to be responded back. Then I sort this list from the slowest to the fastest query that we ran. So, and then I plot this on a chart like this. So this request, this shortest line is my fastest response, and this longer one is my slowest response. So it's always going to look like this. I mean, we don't know, we don't have any measure here. It might be 1 millisecond, it might be 1 second. This might be 20 millisecond, it might be 20 hours. Doesn't matter, but the shape is going to always follow this. Basically, it means a very large portion of the requests are going to be very fast, and they are not going to be very different from each other, right? This is the normal situation of the system. All of the requests are going to be roughly in that area. Oh, by the way, we are talking about a system that doesn't have that much memory to cache any data. So you always go to the disk. So it is going to be something like this. And then there is a very small percentage of the request. Again, this is a small percentage. For a system might be 10%, for another one might be 1%, for another one might be, I don't know, 0.1%. But it is going to be like that. These are the situations, these bad requests, these bad response times happen in situations that, I don't know, there was a failure in the system. I don't know, your disk failed. You had to restart one of the nodes to upgrade the operating system. There was a network glitch. I don't know, it was 9 p.m. and you send a request and Java was taking the garbage out. Garbage collection doesn't work like that, but anyway, you know what I mean. So the garbage collection was happening at the time, so your response was stuck and you didn't get the response back. So these are the bad situations that can happen in any system during a long period of time. So those bad requests are always going to be there. So now, if we put a cache in front of this database, or it can be a cache, external cache that you put in front of the database, or it could be a database that has a caching component built into it, right? As most databases have this caching component. If you do something like that, the response time is going to become like this. Basically, you make the fastest queries that you were running on the database faster, but you don't do much about the slow ones, right? So this basically break here is your cache hit rate. If your cache hit rate, 50% of the requests are answered from the cache, 50% of the requests that were already quite fast are going to become significantly faster, but that 50% that were not fast are going to remain almost the same. They are not going to change significantly. So this is the effect of caching. It doesn't matter if the cache is built in or if the cache is basically an external system in front of the database. So what would be the effect of something like this? So it has many implications, a system like this, but I'm going to talk about 4 of them that I think are the most important one. First one is that when you build applications in front of a database that has these characteristics, it might work on your machine, but when you take it to some other place, it won't work. So let me explain why I'm saying that. So when you're testing your application against the database, this database has a bunch of RAM. I don't know, either you're running, the database on your local machine through Docker, or I don't know, you have a virtualized machine somewhere else. Wherever this database is located, it's going to have a bunch of RAM, right? Let's say you have just 1 gigabyte of RAM allocated to this virtual instance. It still has a few hundreds of megabytes of cache available. So unless you write more data than this 100 megabytes of data, whenever you test your application against this database, you're only testing the cache. You are not testing the database. So you see one performance, but when you take it somewhere else and you have larger amount of data, it's going to behave differently. So you might say that, oh, but I can take it to pre-prod. Pre-prod has more data, has more resources, and whenever I test it correctly. But again, pre-prod doesn't necessarily have the same traffic as your actual application. So the cache is going to be populated in a very different way to the real world scenario. So because the cache is going to be populated in a different way, the things that were written or the things that were that read in the previous test case were different to the actual use case, you are going to see a different behavior to your application. So something might work in pre-production and you take it to production and it just fails to operate the way that you want it to operate. It can be even worse. You can take it to production, everything is fine and it's working even in production. But then suddenly a pandemic happens and people start buying toilet papers left and right, and your cache is going to be, again, invalidated for reasons that you don't know, and then everything starts failing and you wouldn't know why things are starting to fail because everything was working correctly and I don't know, your system was built to scale to the level that you wanted. But now because the cache is being populated in a different way, you might see your application failing in production. But I would say that the worst one is that increasing the size of the cache, it's not going to improve the latency of your application. This might sound a little bit bizarre, but let me explain it. So yes, we saw that I don't know, if your cache hit rate is 50%, you're improving the 50% of your requests, right? 50% of your requests are going to run, let's say, 10 times faster. But the problem is that you're not looking at single individual requests. If you want to improve the performance of your application, you have to improve a bundle of requests. So let's go back to this Amazon page for an example. So how many database calls do you think have been made to render this page? I'm pretty sure there's one call to get the information regarding this thing. There's possibly one call to get the items in my basket. There are, I don't know, some other calls to get the items that were bought together with this. Another call to, I don't know, the 4-star and above related items. I don't know, some similar items here. So yeah, as you can see, you usually create multiple calls to separate systems. It's not necessarily one system. Separate calls to different microservices that each of them might have a different database to fetch the data. So the time that it takes for this page to load is dependent on the slowest running task. So in this case, the sub operation number 5 is taking this long, however this long is, it's, let's say, 200 milliseconds. So that page is going to take 200 milliseconds to load. It doesn't matter that this one is faster. This slowest one is going to dictate how fast the page load time is going to be. So now let's say we put a cache in front of our database or increase the amount of memory in our database so it can cache more data. So the thing that is going to happen is that some of these requests, the sub operation 1 to n, are going to hit the cache and they are going to run faster. So this pink line is basically showing that they are running faster. But if not all of them are answered from the cache, if just only one of them is answered from the disk still, the response time is going to remain the same, right? So the response time is not going to change. It might become a little bit faster, but you are not going to experience that order of magnitude faster that you expect from putting a cache in front of the database. And that is true even if your cache hit rate is 90%. If you are doing, I don't know, 5 operations, 0.9 to the power of 5, it's just going to improve 50% of your operations to the level of cache. 50% are not going to experience much difference. So cache doesn't really improve the performance. So now the question becomes that, okay, if cache is not really improving latency, so why every single database in the market has some kind of caching? And the answer to that is kind of simple. Cache does improve performance, but performance is not only about latency. Cache actually enhances throughput, right? So you can increase the throughput of your database instead of its latency. So let's go back to this picture that I showed you a little bit earlier. So we said that, okay, the requests that are going to the disk are going to take significantly longer than the requests that are going to memory. But there is one other thing here. So half of the, in this one, we assume that 50% cache hit rate. In this situation, only 50% of the requests went to the disk. Another 50% that should have gone to the disk were answered from the memory. And if you remember in the beginning, we said that the throughput of memory is higher than the throughput of the disk. So by putting a cache in front of your database, you can improve the throughput that your application can handle, right? So that's the main reason that a lot of technologies put a cache in front of their disks. And then latency and throughput are not necessarily related to each other, but if you put too much pressure on one item, if, for example, the disk you are trying to read higher than the throughput that it can handle, then the task will be queued. And if the tasks are queued, the latency is going to be increased as well. So we are not talking about a situation that the system is overloaded. In a normal situation that the system is not overloaded, this is going to be true, but putting a cache in front of the database is going to reduce the throughput going to disk and therefore increasing the throughput that your entire system can handle, right? So that's the reason that databases and lots of other technologies have a cache in front of the slower storage system. But well, as I said at the beginning of this conversation, things have changed. So the disks that we have today are around 70 times faster in terms of throughput than the disks that we have 20 years ago that most of the database technologies that you work with were designed. So around 20 years ago, the fastest disk that you could get was able to handle around 200 megabytes per second. And as you saw, a commodity disk that you can buy 10 of from Amazon and receive them tomorrow morning for reasonable price, £600. Those disks can handle 14,000 megabytes per second. So it's 70 times better. You might say that, but yeah, everything is getting faster nowadays. But no, nothing else is getting faster. So the CPUs that we have today have the exact clock speed that our computers 20 years ago had, right? Around 2.5 gigahertz. We can overclock in things, but normal CPUs 20 years ago were around 2.5 gigahertz. Current CPUs are still around 2.5 gigahertz, right? So nothing is getting faster. CPU, you are getting more cores on a single CPU, so you have more processing power on a single CPU, but the speed that it's going through the data is still the same since 20 years ago. It's almost the same about the memory as well. Comparing memory, you can see that, I don't know, the speed is doubled almost since 20 years ago, and we have significantly more RAM on our modern machines in comparison to 20 years ago, but the speed of the memories hasn't changed. But modern disks are 70 times better in handling throughput. And that is crucial. So we said we put a cache in front of the database to handle more throughput with our database. But if you can do something with this extra throughput that is available to you through disk, you might be able to do something better than that. And basically that gives you an idea that what's going to happen if you create a database that doesn't have a caching layer. And that is basically the idea of Aerospike. Aerospike is a database that stores all of your data on disk. It doesn't cache any part of the data in memory, but it provides you with a very, very interesting performance, which I'm going to talk about in a second. So let's go back to this picture again. We said that when we are creating a database, the data store is going to be on disk, our indices are going to be in memory, and we cache data in memory as well. So if we drop the 50% of this, the memory available to the system is usually assigned to the indices, and around 50% is assigned to the cache. So if we now if we drop the cache, we can dedicate 100% of memory to our indices. So if we now, go back to this diagram that we had a bunch of memory and a bunch of disk, in our database, we can do something like this. We can create a massive data structure that has the location of every single data in the database in RAM, and then keep the data in the database on the disk without any data structure. So when a request comes in, you find the exact location of that data to the exact sector on the disk. you find that, and with one access to the disk, you can read the data from the disk, and now you have the data ready to return it back to the customer or to the client. So if we do something like this, the result is going to be something. So we said memory is very fast. And we said that the response time of memory, accessing memory, is going to be in order of nanoseconds. If you have billions of objects in your database and everything is in RAM, well, I draw here a tree, but it doesn't matter. You have some kind of a data structure that is usually working in order of O of log n or n log n or whatever. So it's not really going to uh, uh, it's going to be it's going to be able to find the data that you are querying with a few access to the memory. So you find the location of the data on disk in a few nanoseconds. Then we said that you know the exact location of the data on the disk. The modern disks, other than being very fast, they don't have the problem of random access that we had 20 years ago. You can very quickly access to any part of the disk. It usually doesn't really matter much that you are reading sequentially. And also they are providing with parallelism as well. So modern disk can handle hundreds of parallel reads at the same time. So you can very quickly go to the disk and say that give me from this sector this many bytes, and you read that, and that's going to be in order of microseconds, right? So nanoseconds finding the location on disk, and in microseconds you read the data from the disk and it's now available, and now you should put it on the network to return it back to the customer or the client, and it is going to take around hundreds of microseconds. So hundreds of microseconds, your network latency, a few nanoseconds, your memory latency, a few microsecond disk latency. Putting it all together, the performance of this request will be in hundreds of microseconds. Basically, this nanosecond, because this is hundreds of microseconds, because your network is going to be in order of hundreds of microseconds, you wouldn't see these fast depots. This is the thing that is going to dictate how fast your response is going to be. So the interesting thing that happens here is that something like Aerospike database that is basically have this cache-less mechanism. There's no part of the data in the cache, and going to the disk and going to go to the memory. If you configure Aerospike to write basically to store the data in RAM, so basically work as a cache, which you can do configure Aerospike to do that. If you do something like that, it basically becomes like this. You can store your data in memory as well. And still, this response time is going to be in order of nanosecond, and this response time is going to be in hundreds of microsecond. So the performance that you get from this architecture, which all of the data and the index are in memory, is still going to be in order of hundreds of microsecond. So basically you have two systems that one of them store the data on disk and one of them store the data on RAM. And from an observer point of view, both of them are working in less than a millisecond latency, right? So that's the thing that I said at the beginning, that you can achieve performance similar to a cache, right, without storing data in RAM. This is how we can do it. I have to make some exclamation points here. So first thing is that if you don't have this network latency, if you're not making a database, if it's your local process and you are thinking about reading from the disk and reading from the RAM, well, that's going to be thousands of times faster if you read it from the RAM. So there's nothing much you can do over there. But you can have a database or another system that is sitting over the network that reading the data from the disk and performing similar to technologies that keeping the data in the RAM. And one other thing is that, well, this thing that I said seems very simple, right? You might be wondering why nobody else is doing that. Creating the system is actually quite a complex thing. The idea is as simple as that, as simple as I explained it to you, There's nothing more than this. But implementing this idea that you're having a very large index in the RAM, and you can always read the data from the disk, you can keep the size of the RAM, size of the index is small enough that you are not wasting memory, and relocating the data that is written to the disk efficiently is actually a very, very difficult task, and that's what we've done in Aerospike. But the idea that how Aerospike can achieve performance similar to a cache that stores the data in RAM is basically as simple as I said. And then the other question that you might have here is that, well, if Aerospike is performing very similar to a cache by storing the data on disk, why do we have a mode that we can store the data in RAM? And the answer to that is going to be another talk, but I do have a few articles that in one of them I explain why a cache still might be relevant to your use case, which I'm going to share with you at the end of the presentation. But that is the idea. So basically, Aerospike can achieve a cache level performance without storing any data in the RAM. So, well, what's going to happen if you use something like Aerospike against, compare Aerospike against other databases that you are familiar with, that all of them have a caching layer. MongoDB, for example, have a caching layer. The recommendation is that to have 50% of your data in the cache. So basically, if you have a 1 terabyte data set, that 1 terabyte data set, you have to have 500 gigabytes of RAM available for it to be stored in the database. If you have to have a replication factor of 3, so that 500 gigabyte becomes 1.5 terabytes. And then don't forget that MongoDB also has an index, so that index is going to be in the RAM as well. So all of that is going to be there. For Aerospike, you only need to keep that in. Only need to keep the index in memory. The data can reside on the disk, that, as you saw, is significantly cheaper than memory. But the other thing that would happen is that if this gray line, basically the gray lines that you see here, is a database that doesn't cache the data much, doesn't have enough memory, or doesn't have a built-in caching layer, the performance is going to be like that. When you increase the amount of cache, the performance starts to become like this blue line. But with a database similar to Aerospike that doesn't have a caching layer, all of the requests are going to perform as fast as a database that has a caching layer, unless the part of the data that is not as fast as this thumbs up thing is sometimes distracting. So it's going to be as basically, well, Aerospike cannot do magic here. Bad things can happen to Aerospike as well if there's a network glitch, or if you need to do bad things. This bad things would still happen, but these bad things, because Aerospike is significantly faster, are going to be recovered much, much quickly than other technologies. So, okay, let's recap what we discussed so far. So we said that the Aerospike can achieve performance of an in-memory database, but the data is going to be persistent, right? So you can achieve, well, if you store all of the data in memory, it's going to be as fast, but it's not going to be much slower than storing all of the data on your disk, but the data is going to be persistent. Next level is that it doesn't require a large amount of memory to deliver that high performance. If you assume that the size of index is 1/10 of the size of your data, you can significantly reduce your dependency on RAM, but still get the performance that you want to get. Next one is that your entire data set is going to be accessible with the same response time. So lots of other databases, let's say Couchbase, that is made with the idea of having a cache in front of a database. If you read the part of the data that is in the cache, it's going to be very fast. But if the data is not in the cache, you have to go to the disk, and it's not going to be as fast. So with a technology like Aerospike, it doesn't matter if you written or read this data 2 minutes ago, or written or read this data last time 10 years ago. When you access the database, the response time is going to remain the same across entire data set that you have. So that's another benefit of Aerospike. So in this talk, I mostly told you the story of read-heavy processes. I didn't tell you much about write at all. So Aerospike writes are very similar to the reads. They are very similar to the cache as well. I just didn't go through it because, well, we have a limited time and we didn't want to confuse you with telling you all of the details of Aerospike. But I mean, Aerospike can handle both read-heavy and write-heavy and mixed workload, similar to a cache. So you can achieve that with Aerospike. Next one is that this faster performance doesn't require more resources. Usually when people think that we want to run something faster, people think about adding more resources to the system. Aerospike doesn't need more resources. Actually, it's a very interesting thought process about computers. The only way that you can make an application faster is by making it use fewer resources, right? So an algorithm that requires fewer CPU cycles is faster than an algorithm that requires more CPU cycles. So basically, Aerospike is faster because it is using fewer resources, right? It uses fewer accesses to the disk, it uses fewer amount of RAM. It's because of that it is significantly faster. And then lastly, because it is using fewer resources, it is more sustainable. You know, all of these resources, production of these resources are producing a lot of CO2 emissions, and also running these resources are going to use a lot of energy, and energy production produces CO2 emissions as well. So by using a more efficient and faster solution, we can reduce the amount of emissions and make your company more sustainable. This is, as I promised, these are 3 articles that, well, bits and pieces of this talk are discussed in them. There are more information in it as well. I think it's the middle one, is caching is still necessary, that I'm talking about that. Well, there is still some use cases for caching, storing all of the data in memory. If you're interested, you can read that one. I think Sebastian is going to send you an email with the links to this to these articles as well. And with that, thank you very much. I'm happy to answer any questions you might have.
Barett, yes, I think it's great that there's so much more content potential for more webinars, to be honest. But through different channels, I did get some questions. I think a very classic question here is what types of companies typically use Aerospike?
So there are many different, Aerospike is a company that is trusted by many different technology vendors. I mean, you can check our website, from companies like PayPal to Barclays to, I don't know, lots of other very famous companies are relying on Aerospike. But I would say the typical companies that are using Aerospike are innovative companies that want to compete in the market and provide the best performance to their customers. So you can see people in financial services relying on Aerospike. We do have companies working in more modern type of financial services like blockchain and Bitcoin using Aerospike. We do have ad tech companies heavily relying on Aerospike, multimedia companies, gaming companies. Well, I don't know if you're young enough to know what a Snapchat is. They are using Aerospike heavily in their systems. So yeah, many companies are using Aerospike.
This is great. Another question which came up, is what kind of infrastructure is needed to run Aerospike effectively?
Yeah, so Aerospike is not really dependent on any specific hardware as long as you give it modern disks, and by modern disks I just mean SSDs. Aerospike doesn't work really well with spinning disks, but as you possibly know, spinning disks are very old technology now. I haven't seen any new spinning disks in the market in the past 4 or 5 years. So as long as you have a modern disk SSD, preferably with the NVMe interface, Aerospike would work with that, and it wouldn't have any problem. You wouldn't have any problem running that on your laptop or running it on a server or any cloud provider.
Okay. And then here someone seems to be already thinking about running Aerospike, because the question here was how challenging is it to run and maintain Aerospike?
Oh, that's a good question. So, well, Aerospike is a distributed system. We didn't cover the distributed part here. So it's a multi-node system, and you can scale it up and down very quickly and very easily. So that's one side of it. But also, Aerospike has this unified architecture. It's just one process. Most databases have lots of different processes that you have to run, and if one of them fails, part of the functionality of the database will be missed. Aerospike doesn't have that. Just one process. You run it. It's working fine out of the box. You don't really need to tune it. It's written in C, so there's no Java garbage collection tuning. It just works. You don't need to do much. As I said at the beginning of this talk, I've worked with lots of different database technologies as a developer, as an administrator, and I've worked for several database companies in the past 7 years. I would say that Aerospike is very easy to run in comparison to the other technologies.
Okay, this is good news. And then my question is, if it took you 1 hour to create the rocket on slide one, how long did it take you to design this inspiring last slide here?
Well, I did it myself. Well, possibly, I just went to ChatGPT and I wrote a line, and ChatGPT created this beautiful thing for me. But
Very
yeah,
cool.
not able to uh, uh, spell correctly, but the picture is quite cool.
Yeah, it is. Yeah, thank you, Barett. And before I will let everyone go, I have some announcements here. Let me just share very unorthodox my screen. So here you can you see my screen? Upcoming events, Barett? Yes.
Yeah.
Well, I will share this page with you. I just want to be a little bit practical. You guys can always update yourself what's going on. For example, here, obviously, the webinar where everyone participated. Then there's the meetup we were talking about, why I am here in Barcelona. Also, more than 100 people already joining in the Criteo office, one of our biggest edtech customers. This will be great. Tomorrow at TomTom, we will have a great meetup. Also, more than 100 people. TomTom will also explain their story, how they're using Aerospike. And then, yeah, also in the US and in New York, our founder Srini will have a meetup. Just 6 hours flight from Frankfurt. And then next week, there will be another webinar on a global level with someone from Forrester and Aerospike. So just for everyone to know, please have a look at this on a constant base. And yeah, you will know what's going on. Plus, this will also benefit you because we have a really nice LinkedIn page. Here you can see Barett already promoted by Aerospike. And yeah, you can find a lot of cool stuff here, not just events, but also a lot of content. So please sign up. I will send these two things right away now after this webinar. And also in the coming days, I will share the recording with everyone. And that should be it. Yeah, very 1 hour almost, but it seemed much quicker. Thank you, Barett, for making that so interesting webinar. And let's do it again.
Oh, thank you very much.
Not to
We
not to
will have
lose
a
any
meetup.
trust in you.
So we will have a meetup tomorrow in Berlin. If you're based in Berlin, we can come in and listen to the exact same talk live. But we will have yeah, we will have more content coming up. In November, we are going to be in Stockholm for another meetup. I'm preparing another talk. Also, well, you saw some of the articles that I've written around this topic. I have another article that I'm writing at the moment, which I'm going to talk about one tier and multiple tier response time systems. If you're interested, follow our Aerospike page. It's going to be published there. You can add me on LinkedIn as well. I'd be happy to have you in my connections, and you can follow up those conversations as well. And yeah, thank you very much.
Okay. Bye.
Cheers.